Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another Engineering Mechanics lecture video. This time we're going to look at reduction of a distributed loading, so let's get into it. Firstly, the lecture objectives. Firstly, to understand distributed loads and how they're described, and then to find equivalent force and location for various distributed loads. So just firstly, some examples include wind loads on structures, for example, signs, towers, buildings, and so on. Water pressure on tanks, dam walls and submerged bodies, and granular materials in storage containers and conveyors. So in all of these cases, it's often convenient in analysing the structure that's designed to withstand these loads to reduce the loading to just a single force and its location. So similar to what we did before with simplifying multiple forces and moments into a single force, we can do that with distributed loads. So starting off with semi-general case of a pressure loading. So if we have pressure over a surface caused by, for example, grains in the back of a truck, that would have a pressure on the structure, on the walls and the floor of the bin. If we take the special case where in the, what direction is this? In this direction, normal to this plane here, so across the width of the beam in this case, if the pressure is uniform, then we can simplify that to just be a coplanar distributed load, and we'll say that the loading is a force per unit length, whereas with the pressure we have force per unit area. Okay, and the general distributed load is described by some function or as a function of x. So note that this is not multiplies. This is saying that the distributed load here is some function of the position x along the beam. And if we have uniform pressure across the width, then to get the loading per unit length, we can just multiply the loading per unit area by the width. And then eventually we'll see over the next few slides that we can replace this by just a single force, and we'll also need to know where that single equivalent force is located. As I said, the distributed load force per unit length described as W as a function of x. So the total force, or the resultant force, is the sum of all of the little forces along the length. So using calculus, we split up this distributed load into small sections or small lengths dx, and each of these small widths or lengths dx has a small force df. Okay, and that force will be equal to the value of the distributed load at that point times the width dx. And that's also equal to the area of this little strip here. Okay, so just a reminder of what you did in Maths Modelling 1 and probably at high school also, where you did integration and differentiation. So that's what we're just doing here, but applying it to the context of analysing distributed loads on structural components. Right, so the total force is equal to the sum of all of these df's, and the way we do that for a continuous function like this is to integrate. Okay, so you should remember that integrating is the same as finding the area under the curve. All right, so our resultant force here is equal to the sum of all the little forces df, and we add them up for a continuous function by integrating. We saw that df is equal to the value of the distributed load function times the width of the element dx here, which is the same as integrating over all of these dAs, which is the same as finding the area under the curve. Okay, so our resultant force is equal to the area under the distributed load curve. which is what I put there in the slide. Okay, so now that we know how to calculate the resultant force, we now need to work out where it acts. Okay, so we do this in a similar way to what we did previously. We look at the moment of each force dF, right? So our little elemental distance here, or width dx, and force dF. The moment of each of those about O is x dF. So for this little strip that we've got here, its moment about point O is dF times x, and we saw that dF was this value previously. So now we just need to sum all those up. So taking moments about point O for all of those, that's the same as integrating, adding up all of these lengths dx, same as integrating, and the moment effect of the resultant force is Fr times x with a little line over the top that we call x bar. Okay, so from before we had this, so if you'd forgotten that, you can go back to the previous slide and just see where we got this from. And rearranging all of that gives us that x bar is equal to the integral of the moments divided by the load. Okay. So previously we had distance is equal to the moment, the resultant moment divided by the resultant force, essentially what we're doing here. And then, as we saw before, if we're integrating, we're essentially finding the area under the distributed loaded curve. Okay, so this location here, x bar, is equal to the integral of x times all the little dAs divided by the total area. So don't worry too much about this. I'm not going to make you do the integral in this subject, but it is instructive to know where what we do next comes from. And if you do need to apply, or if you do have a situation where you've got a distributed load that looks something like that and is defined by some function, then you've seen how to go about solving that. And there's examples in the textbook that you can have a look at as well. Typically what we'll do, and in most engineering problems, the loading curve is a simple shape such as a rectangle, triangle, could be a parabolic or ex-parabolic area, could be trapezoidal area, which you can make up from a rectangle and a triangle, as we'll see. And the centroidal position is given from tables. So what we calculated previously was the centroid of this area. So you would have hopefully done centroids back in Introduction to Mechanical Engineering and maybe even Maths and Physics. So yeah, this is just a revision, I guess, of that. So you need to know about the centroid of an area or a shape, and that's what we're going to use in working out our resultant force. So we can just look up these tables for the centroid and the area if you don't remember those formulas for area of simple shapes. So let's have a quick look at a simple example. So we've just got this beam here with a distributed load, which is linearly varying from 0 to 3 kilonewtons per meter back to 0 at the other end. And we want to work out the equivalent resultant force and where it acts on the beam. So we've got two triangles here, so we can just use the triangular area. These are in the appendix in the textbook, or you can look them up online. There's probably hundreds of websites that will list all of these properties of common shapes. All right, so we've split up our loading into two triangles like this, and each of those two triangles will have a resultant force or resultant load, and we can work that out simply by working out or calculating the area under the loading curve. All right, so we know the area of a triangle is half the base times the height. So the base here is 3 meters. The height of the triangle is 3 kilonewtons per meter. So a half 3 times 3 for this one. And then on the right-hand side, half the, I'll just swap these over here. So I put the height first and then the base second in this one. So then now that we've got those two, we can work out our resultant force F just by adding those up. And we get the resultant force of these two distributed loads is 6.75 kilonewtons Now we need to work out where this resultant force acts, because if we're going to work out, for example, the moment at the end here, the reaction moment, then we'll need to know that in order to do some of the moments. Okay, so some of the moments about point O, we have FR times X bar. So I think I'll put that there. Yeah, so X bar, or the centroidal, not really the centroidal location, but it's the location of the resultant force. So we can work that out from some of the moments. So we have the force for the left-hand side triangle distributed load here. Now, this force acts through the centroid of the little triangle here. So we can go to our diagram, our table that shows us the properties of general shapes, and we can see that from you kind of need to rotate this on its side. Right, so the distance from the base to the centroid, if we're coming this way, coming horizontally, base is here, so a third of this distance along here. So from point O to over here will be 2/3. And then similarly for this one, base is here, so the position along here will be 1/3 of this length. So that will be 1/3 times 1.5. So having obtained those two forces and their perpendicular distance and summing the moments about point O, we end up with an expression that has only X bar as our unknown, right, which allows us to work out the location of this resultant force. So if we do the maths, we get X bar equals 2.5. And I think that's it. All right. Okay, so that's it for simplification of distributed loads. Mostly, as I said, we won't need to do the integration, we'll just use simple shapes, and we'll do some more examples in the tutorial. So hopefully that was helpful, and I'll see you in the next video. Bye for now.